All right, welcome guys. So today's lesson is going to be about shaders. So shaders are essentially just kind of a catch-all term for something you can do that's usually run on like a graphics card that will be split into like a bunch of subtasks. So typically what that means is if you're trying to render an image, for example, a shader would handle every single individual pixel one at a time. So if I wanted to I don't know, draw a gradient across a screen like this, I could write a shader that says like, okay, based on my position on this screen, color this side more white and then this side more black. And then based on like some math that you do, you could like get kind of a cool gradient going across there. So that's like a very simple example of something that you could do with a shader. It essentially means that like if I were looking at this specific pixel, I could take in data about it and say like, I'm at position X, Y, and I have some, I don't know, like color data or something like that. And based on information that's passed into the shader, it'll process it and output some value that can then be used to render an image. So typically in a general graphics pipeline, what kind of happens is, and I'm going to be simplifying a lot of stuff here because you guys don't really need a lot of the details. If you want to learn more of the details, I would definitely recommend taking CS 174A because that will teach you a lot more in depth than I will cover right here. But essentially what a computer rendering pipeline does is when you're looking at a scene that's rendered in like Unity, for example, you're going to have, and I'm talking specifically about 3D scenes here. There are different render pipelines for two-dimensional things. So we're specifically talking about rendering 3D scenes here. So typically you'll have a bunch of objects in the scene that are composed of meshes. So we talked about meshes last week. Essentially what they are is just like a collection of vertices and edges that all define a bunch of triangles that are in some shape. So if I have some box like this, it'll be just a set of a bunch of triangles, or I might have like a sphere that's really just kind of broken down into a bunch of smaller triangles, blah, blah, blah. You get the idea. Essentially, like any shape that you want to have rendered will be done so by composing together a ton of small triangles like this. And essentially, how you can define a world space like this is by using a bunch of math, essentially. So I can start off by saying like, okay, let's imagine I have some sort of coordinate system of just like X, Y, Z. So I'm just going to call this X, Y, and Z. And if I want to put, let's say like an object up here, I'm just going to use a circle as an example. I can define this guy's position as some shape like this, and this will just be at some like X, Y, Z position. And essentially, this is its coordinate relative to some origin position. And what I can do from there is I can then define a camera that kind of uses the origin and the position of objects in the scene to actually render an image. So what'll happen is I'll have a camera, let's say I put it like over here at some other position. And what the camera will do is it essentially just kind of draws a big region of what it wants to turn into an image. So for example, if I want to kind of capture from this camera off in this direction, I could kind of draw a screen out from this area and kind of figure out what I want to do with it. So what ends up happening is you can kind of draw 4 vectors out from the position of the camera to end up getting what's called a frustum. So we end up usually chopping off a bit of this so that you don't get like weird clipping with the camera. But essentially this kind of like sort of prism shape, I don't know what you would want to call it, this frustum defines the region in which you want to like render an image. So whenever you're looking at a scene like this, for example, you can imagine if I like click on this camera, for example, I'm not sure why it's not displaying the frustum as it is. Yeah, okay, yeah. So you can kind of see like there's this whole region that's defined by this camera that kind of is similar to what I drew before. This is the frustum of the camera. So everything that's within these bounds is something that will be rendered to the camera. So essentially what it's doing is it's within these bounds, figuring out what objects are in the scene. So for example, all of these different cubes here are within the bounds of this camera. And it's grabbing all of the triangles from those objects and doing a bunch of different stuff to them to kind of define how to actually draw them. Is this making sense so far? It's like a thumbs up or anything. Cool. And there's a lot more like technical details to it, but essentially from a conceptual level, this is how a camera works in Unity. So the first step of a render pipeline is essentially figuring out what is in that camera space. So there's a bunch of math. We're going to skip over that for now because it's not super relevant. Again, if you want to know what all that is, take 174A. But basically, you can do a bunch of matrix multiplication to kind of figure out like, okay, I know what defines these bounds here. Excuse me. And I know that this is within those bounds, so I want to render this object. So what does actually rendering that object mean? So when you're looking at, say, if we have like a sphere here, for example, we know that it's composed of a bunch of triangles, right? So essentially what happens is for every single triangle that the camera can see, it will go through and define a plane on that triangle. So what ends up happening is from those 3 points, you can imagine like I could define an entire plane. And what's done is that every single one of these triangles on this object will be defined in this way and kind of trimmed to the actual size of that triangle and colored in some way that is defined by a shader. Thus, it's like shading in the region, right? That's kind of where the term comes from. So there's a ton of different ways to do this. So typically it's done by sampling from a texture, for example. It can also be done by sampling from just like a direct color value. You can add in lighting information that's based on like where the camera is relative to a light source. There's a ton of different information that can be added onto a shader, which is why it's kind of like a catch-all term because there's just a lot of different things that you can do with shaders. So this would be an object shader or yeah, it'd be an object shader because it's attached to the actual object. There are also what are called post-processing shaders, which I believe Athena covered partially in the art tutorial this week. It's essentially stuff that once you have a rendered image, put some effects on it afterwards based on what that image is to kind of change it up slightly. So again, shaders are a very broad term and they're kind of used for a bunch of different things. So what we're going to do right now is just kind of like walk through a very, very basic example of like the simplest shader possible, which would be just, well, there's probably a simpler shader, but just imagine you have like a box and I just want to color in every pixel on this box, just pure white. So I guess I'm not using white, but the idea is that like we want to just kind of take this whole box and make every pixel on it white. So how the computer basically does that is it knows the vertex positions of all of these objects and all the triangles. And what we're going to tell it to do is based on where all of these triangles are, basically if a pixel is in that region defined by one of those triangles, we're just going to color that entire pixel white. And that will kind of repeat across this entire object. And then we'll end up with a fully solid white object. So right now I gave you guys a link to this whole scene. This I'll get kind of into later. Because I want to just kind of go over the basics of like what a shader is, but like this would be an example of a post-processing shader that's kind of taking information from the scene as it is and doing other fancy stuff with it with this like wave effect. But like this is a more complicated example of like what a shader can do. Whereas the kind of shaders that I'm talking about right now with like coloring objects would be the sort of shader that's on this cube, for example, that I've kind of deformed into this other shape. I don't know where my camera is like bugging out here, but anyways, excuse me. So how shaders are generally stored in Unity is attached to an object's material. So if you look here, this cube, for example, in its mesh renderer has this default material object here. So if I pull up Unity and just kind of click on this, I can select from all of the different materials that are in this scene. So these are a lot of the default ones that just kind of come pre-built in Unity. So if I wanted to like change the material, I could select that one, for example, and you can see that it starts kind of rendering differently. Why is it like zoomed in so much? Sorry. Not sure why it's like bugging out for me. But okay, so you can see when I change the material there, it now is using like a different rendering method, and it kind of like changes the color of it. So materials are often defined like per object if you have to like map a specific texture to it or do different things with it. But what's actually on this material is a shader. So for example, if I look at this material that I defined for that like cool sound wave effect, you can see, or let's actually back up a bit. So I'm going to just make a new scene because this is a bit easier to explain from here. So we're just going to go over here, just into my scenes folder, and just create a new scene. And I'll just leave it as like, let's call it like test or something. We'll open it up. Just going to save what I have here still on. Why is my camera like not? I might restart Unity really quick, but it's moving around way more than I want it to. Okay, I'm just going to add a empty game object. Sorry, I'm going to add in a cube, for example. So we'll focus on this. Oh, that's better. Okay, I'm just going to put its position back to 0, 0, 0, so it's not like all random there. Okay, so yeah, we have a cube here. And you can see we have this default material on it. So if we select the default material, you can open it up and see there's just a bunch of different information about it. Not super relevant because we're about to make our own material here. So if we go into our assets here, I can go and create, and then I'm just going to start by making a shader. And we're going to start with an unlit shader for now. And we'll just call it like my shader. And we're also going to, actually, no, let's not do an unlit shader. 1 second. Let me double check something. So I'm like referencing my notes really quick. Sorry, 1 second. Okay, yeah. So we're going to stick with an unlit shader. And I'm also going to go create and then insert a material. And I'm just going to call it like my material. Okay. It doesn't really matter. And all I have to do to apply the shader to the material is just drag it on top of it. And now you'll see that the shader takes all of its properties from here, which for the default one just has a texture, and just applies it onto the material. So now you'll see that there's like a texture here, and then there's some other information that's like specific to the material. But essentially what we've done is just like attach the shader to this material. And now if I were to drag this material onto the shader, you'll see, or onto this object, now you'll see when I look at this cube, it has taken on my material. I probably should have not named it my material in retrospect. Anyways, it's using my material, and you can see that it's just rendering a blank white color. So why is it rendering this blank white color? Well, let's actually just kind of take a look at the shader and sort of walk through exactly what's going on inside of it. So if we open up,
question,
yeah.
Can you show us the game view? Like I see that there's some. Okay, yeah.
So right now it's asking for a texture. I don't have a texture attached to this, so if I were to just like, I don't know, grab that for example, you can see now the cube has this checkerboard pattern texture applied to it. Or I could do all these different things. Essentially, it's just kind of mapping whatever texture I give it onto the shape. So I'm going to leave it at none for now so we can kind of walk through and see what it's doing. So again, I'm going to right click on my shader. I'm going to open up C# project, and that should open it here. If it doesn't, then what you can do is just kind of drag and drop it onto Visual Studio, and then it should open it. If you're having trouble, just like open a script and then drop it in. I'm not sure. I might be stupid right now, but I think there's some way to open it specifically. Oh yeah, right here. Yeah, so if you hit right there, it will open it up inside of Visual Studio. Excuse me. Okay, so now we're actually looking at the code of this shader. And this is going to look a little weird because it has some very strange syntax to it. So this is, I believe, an offshoot of OpenGL. I'm not sure if that's specifically what it is, but essentially it's just like a specific language developed for shaders. So there's a lot of like weird information that gets kind of thrown into here, but it's relatively well organized. And there's a lot of documentation on the syntax that you need for this. But I'm just going to kind of roughly walk you through what we're looking at here. Okay, so obviously we're defining our shader up here. And then every shader has a list of different things that can kind of go into it. So for example, this basic shader has a properties thing right here. So if we look right here, we have our main texture that is just called texture. It's a 2D texture, and by default, it just goes to white. So a lot of these are just kind of like preset values that are defined by the render pipeline and by the shader language. So essentially all this is saying is that like, I want this shader to use a texture that is by default white. But that also means that if I look over in Unity, you'll see that this property is actually on my texture value here. So if I were to like apply a texture onto this material here, that's the reason why I can do that, because our shader has this property in it. So if I wanted to add in, for example, a color, I'm just going to copy paste some code from over here. Just really quickly, and I'll walk you through it in a second. So if I wanted to make, I'll just call it color equals color. And then this is just an RGB value and I believe a transparency value. I'm not sure. It's a vector for
yes, can
that
confirm that's transparency at the end.
Okay, cool. This essentially just defines a variable name, tells you what you want it to say in the inspector. Tells it that it's a color and then defines that actual color value. So by default, if we have RGB set to all to 1, it'll be white. So I'm just going to go ahead and save my shader now. And you should see, should I refresh it? Why is it not updating? Okay, yeah. So if I look into the, I guess that doesn't show it here, but if we look into our material, now we actually have a color value, which we can select just in the editor. So that's how you can add different variables onto your thing. So for example, with my sound wave effect, I have a main texture. I have just a value that's a float to deal with like how wide the bar is, a bunch of other stuff, a bunch of colors. Essentially, this is like your list of all the variables that you want to link to your specific shader. Okay, so properties, that makes sense.
Question.
Yeah.
How come the color didn't change on screen when you changed the color in the editor?
Because we haven't actually done anything with this color value. All we've done is, this is just like defining a variable. So we've just defined that we want our shader to have a color value, but nothing in this code actually tells it to do anything with that value.
So is basically the syntax here is the first thing is you're defining the data type. The second thing is the name.
So this
variable?
Is the variable name. This is the inspector name. So if I were to change this to like, blah, you should see it update in here. Yeah. We'll leave it as color for now.
So there's a separate variable name and inspector name. That's interesting.
Yes. If I can type, we'll leave it as color. Then
the third thing is the type.
Yeah, that's the type. And then this is the actual value that you give it. And then what else was I going to do? Right. Okay. So we've defined a variable, but we haven't assigned anything. So now if we look into Subshader, this is actually kind of the meat of what is happening. So this stuff isn't too relevant right now. I'll go into that. I'm probably going to skip over this for now. Essentially, tags, I believe, I don't actually know what that is, if I'm being honest. LOD is level of detail. That's like a different concept that we don't really need to cover right now. What we do care about is pass here. So pass is a portion of Subshader. And basically, this is what this code inside of here is what will actually deal with rendering the color or rendering the pixel that you're working on. So right here, we're defining these two things, pragma, vertex, vert, pragma, fragment, frag. This is just to kind of make things a bit easier to work with. But essentially, the meat of what's actually happening is this function right here. Or sorry, this function right here. So you can see this kind of weird syntax is fixed for. This is essentially just kind of like a float that is a little less accurate, which is good because it means that it will run faster. There's less computation that has to be done. Fixed for is like a 10-point floating point number rather than a 32-bit, or sorry, 10-bit versus 32-bit. So it's just like less accurate, but it's because you're doing it across so many different pixels. Like if you're rendering like a 4K monitor, for example, that's a lot of pixels you have to work with. It's better to do a lower accuracy thing so that it runs faster. But anyways, that's just a variable type. And then frag is in reference to a fragment shader. So fragment shaders are, again, shaders that involve rendering specific pixels. So essentially what this whole shader is going to do is it's going to go pixel by pixel and render what we're doing. And we're just saying that by putting frag here, this is the actual function that will be running on everything. And then we take an input of v2f, which is, this is just essentially a struct that we're defining in this. And then I is just kind of like the actual pixel data that's being passed in. And then SV target is where that output goes. It's essentially just a buffer that stores all this information and then eventually renders an image. So there's some steps in between that we're kind of skipping over, but essentially it's this whole pipeline of taking in a set of information and then outputting it to, or running some functions on it, then outputting it.
Okay, does anyone have any questions at this point?
This is a lot of information. So, and I am kind of rambling here, but hopefully it somewhat makes sense so far.
Yeah, I have a question about the, you said that frag stands for fragment shader, and that means that you're shading individual pixels at a time.
Right.
Does that mean that there are shaders that don't do that?
So the other type of shader would be a vertex shader, which essentially that is, if you remember back a couple steps to when we were like defining what's inside of the camera, that would be what a vertex set is, or sorry, a vertex shader is doing, is essentially like running all those calculations, trying to figure out where the vertices are in the camera. So typically you're not going to be working with anything that is at that level of detail. But yeah, so it's basically vertex shaders and fragment shaders. So anything that is to do with visual effects will almost always be a fragment shader.
Okay, all right, I see. Thank you.
Yeah, no problem. That's a good question. Okay, any other questions before I continue?
I guess I was wondering, like, if you wanted to make shaders yourself, do you have to basically learn the coding language that the shaders are written in, or is there like ways to do it without code, like some like kind of thing in Unity that's not?
So there is, I would actually recommend using this tool. It's called Shader Graph. It's built into Unity and it's like way easier to use than all of this, but I think it's also very useful to know exactly like at a fundamental level what's happening with the shader, which is why we're going over this. Cool. So we might go over Shader Graph in a future tutorial, just to show you like, this is the hard way of doing it. And then this is the easy, like fun way of doing it. But I do think it is important to at least like have an understanding of like what's going down inside the actual code so that you can kind of understand like when you're moving a bunch of stuff around, why that's working, which is why we're starting with this, even though it's kind of complicated. Anyways, cool. Any other questions? Nope. Okay, cool. Okay, so again, this function is taking in this v2fi. I believe v2f stands for something I can't remember, but basically this is just doing some stuff that we don't really care about. It's just pre-rendering to make sure it's like not clipping into anything. Transform texture. Honestly, I don't know what any of this stuff is off the top of my head, but most of the time you don't have to care about most of the setup stuff because you won't be the one writing it. It'll be kind of filled in by default for you. What we do care about is actually the struct v2f definition right here. So this is actually what will be passed into the shader. So you see we have this float to UV, which is our texture coordinate. So all of these like all caps things are variables that are predefined by the shader and refer to like specific data that is accessible by any shader essentially. So every time a frame is rendered, every pixel will have some like texture coordinate associated with it, or like, for example, this SV position and stuff like that position. All of this data is just kind of stored on the system, and all we're doing is just accessing it per pixel. I can go a bit more into detail about that, but if I'm being honest, like I'd have to refresh myself a bit more. So if you're curious about that, I'll talk to you about it later when I like catch up on it. But essentially all you need to know is that like we're defining the struct of what we want to have passed into this data, as well as I'm not sure what this app data is you can use for. Oh yeah, so this is also other data that will be passed in. This does some like pre-functions on it, and then we pass that into our actual fragment shader, which is doing essentially the fun stuff. So most of this is just kind of structural code to set up this whole function. So the frag function is like all you really care about, and that's all we'll kind of focus on for now. You can get more into detail on like what data you want based on like what shader you're working on, but for the most part, the cool stuff happens here. So you can see there's just two functions that are called here. There's fixed for color equals texture 2D of the main text and i.uv. So all that's saying is basically, if we remember back to last week when we were talking about meshes, essentially, if you're trying to texture a mesh, you'll have this texture that is called a UV map that has like some flattened out image on it, I guess. And it can be defined as a set of coordinates from 0, 0 to 1, 1. And every pixel will have some corresponding, this would be our U, this would be our V. Every pixel will have some UV value to it. If I can write. That corresponds to where it is in this plane and where it should sample from. So I guess if I back up, like all this is kind of handling like writing out where that UV position is and like getting it all correct before it's fed into here. And then all this is doing is just saying, grab my color and use, so text2D basically is just like a pre-built function that grabs the main texture, which again is one of our properties. So we could feed in a texture here, and then grabs the UV of our specific pixel and just grabs whatever color is there. And then this fog thing is just like, Unity has like a built-in fog effect. That's why it has the Unity before it. We don't really need to care about that right now. I can actually just get rid of this and it wouldn't probably affect much. So I'll do that for now. And you can see it returns color. So literally all it's doing is just grabbing the texture, putting it, grabbing the texture based on like where it wants to render it, based on the mesh definition, and then just returning it. And as we go back in here, if you remember back when I added a texture onto here, if I just put like this default texture on, for example, essentially what it's doing is it knows like this face, for example, would map like this corner to 0, 0 and this top corner to 1, 1. And then it just kind of selects from this texture the color value that's on that pixel. And that's essentially how it's rendering everything. Does that make sense? Cool. Any questions?
I was just going to ask, is this what's done for any texture in like 3D games? This is the way it's
essentially done? Yes. Maybe not like this specific code, but like conceptually that's what's being done. Right. Is that you have some mesh, every vertex on it has some UV coordinate defined with it, so that here, I'll kind of back up a second. So if we have there it is. Scroll down a bit more. It's like a symbol shape.
I guess what I'd say is, you remember that in the first tutorial, the example you gave of the Mario mushroom thing? Like, how would that play out in a texture like that?
Let me pull up that image so I can explain it off of that, because that will make more sense than whatever thing I'm about to draw right here. Let's see. Sorry, I'm like looking through my search history trying to find it. Okay, cool. Let's just drop that in here. Oh, cool. Okay, so this is just like an example. So essentially, if we look at, where did I put my pen? There it is. Let's say we're looking at like, I didn't mean to draw that. Whatever. Let's say we're looking at like this vertex, for example. Essentially, this vertex has a UV coordinate that maps onto somewhere like right there. I don't know if that's the specific one, but every vertex on this mesh will map to some point on this 0, 0 to 1, 1 mesh. And that's how the texture is sampled. It basically, like if I'm looking at this triangle, for example, here, that would probably map to something like up here. And the computer is able to kind of like interpolate based on these 3 positions, any position in this triangle that's defined there, and then snag the texture value or color value from there. So that's kind of what is being done to render a texture onto a 3D mesh. Does that sort of make sense?
Yeah.
Cool. Little bit of a side tangent, but it's helpful to know. So we're going to do something even simpler than that. Rather than grabbing from this texture and doing all this complicated stuff, we're just going to directly set it to our color value. So for example, we define this color here. So what I'm just going to do is instead of color is equal to that, I'm just going to set my color to color. And now, if we go back to here, you can see that if I go to my material, I should be able to set the color. Wait, what am I doing wrong here? Let me see 1 second. I save it. Oh, I need to get rid of the texture, I believe. Why is this not working? This worked when I tested it earlier. 1 second. Need to read through my notes again. Did I make a typo? Oh, right. So check this code really quick. Right, okay. I define this as color. I think this needs to be a hash 4. Let's change this to this. And then I'll leave that in there. There we go. Okay. So colors are of half value type or half 4 type, not whatever it was fixed for. But now if we go in here, it should change or not. Okay, I'm not sure what's going on here. But essentially the point I'm trying to make is that like, oh, it's because I didn't change. There we go. Hopefully that works. Nope. Okay, let me double check something. Sorry.
I click on the shader in Unity, it says that there's some errors on it in the inspector.
Oh,
that means anything.
Ah, undefined identifier. Why is it not recognizing it? That's odd. Sorry, we're doing this on the fly, guys.
I just got back. What's going on?
Oh, I believe it's because I didn't define something. Right, okay. I need to, in pass, define color as well. So I need to add in fixed for color. So this automatically will grab this property value and then fill it in there. This is essentially, you have to like redeclare the variable essentially to grab the data. And then if I set this to color, then we can go back into here and now it works. Okay.
This is within which part of the code?
Within the pass. So I just kind of dumped it here after the include part. But essentially, if I were to do like, I'm not sure what the type is, but like if I wanted to like add another color here, I'd rename it to a different variable and I'd have to define it within my pass so that it knows to like grab from this value. Because what was happening there is I didn't actually define it, so it didn't know where to grab this information from. Whereas main text was defined right here, so it was able to grab from it before. So now I can like go into my material and actually change the color. And you can see there's no kind of shading or depth to it or anything. All it's doing is just grabbing the color and filling in all of those pixels. But it's pretty simple just because it's just like literally just setting everything to a single color. Okay. So that's the very, very basics of how a shader works. Now I'm just going to kind of walk you through a more complicated example, that being the sound wave effect that I had done. I'll just save this for now. So this was...
Wait, question mark.
Yeah.
How hard is it for you to like turn that shader that you just made, which was very like, you know, like you said, had no shading or like depth to it, into something that does have that?
Let's try walking through that. Actually, let me see if I have an example of the code somewhere. So, okay, I will say, like, typically if you're doing something simple, someone will have already written something that's more efficient than like anything you could write as a shader, and you can probably just immediately grab that and drop that on your object. But it is kind of useful to know exactly like what's happening. So let me try and find like I want to do, let's say, like a lighting effect onto it, for example. Sorry, I'm like scrambling through my notes right now.
Can you go back to the code? I want to
Yeah,
see
yeah.
what the top looks like. Can you go to the top?
Sure.
Sorry, I just want to see.
Yeah. So because we also, sorry for scrolling down really quick, but because we replaced the texture thing, a lot of this actually isn't as necessary anymore because we're literally just filling it in with a single color. But let me see. I'm trying to think of like a good example of like a cartoon shader or something like that. Essentially, you have access to a bunch of other information about pixel data based on what you're rendering on a mesh. For example, you might know where the normal of a surface is. So for example, like if I'm looking at this surface right here, the normal would be kind of going off in this direction. And what that can be done or used to do is calculate some very simple lighting effects. So you can see, like, for example, I have this in my scene, which is a light source. And what's happening is based on a normal's relative position to this light source, if I were to like rotate this around, for example, in the Y direction, you can see all the shadows update with the Y value, because what it's doing, it's grabbing the normal value and calculating some information based on it to render these shadows. And like you can see this texture gets darker when the light turns away from it because the normal is blocked by kind of what's above it. There's a bunch of other stuff. I don't really want to go into the detail of the math behind that just because it will take a while to explain. But that's like an example of like how this shader is more complicated than the one what we just did.
So how in your own code do you like implement lighting into your shaders?
I'll just kind of say like you don't really want to do that at a shader level on your own. You're better off just like using some pre-written code. But that would go into essentially this function here. You would grab data about, so from like a high level, you'd basically in your input data, which is this struct here, you'd grab data about the normal of what pixel you're looking at. And you'd also grab data about, actually, I think you just need the normal essentially. And you need information about where the light source is as well. But that can be grabbed from the camera somehow. I don't know the syntax off the top of my head, but essentially you grab some extra data and then you just run some calculations in here based on the normal value and kind of the direction of reflection of the light. And then you can, for example, if I wanted to like make this color darker, I can multiply it by some value. Actually, this might be a good example. Let's go back a second. So instead of, let's try doing that gradient effect that I had like mentioned before. So we could do our color value, which by default is just whatever color we input it as, and we could do it as a multiple of the UV position, in some sense of like normalizing it for its distance. So you can imagine like, sorry, I apologize, I'm just kind of rambling here. I'm just kind of coming up with this as we go along, but hopefully this is like somewhat informative. Let's get on here. Where did I put my pen? So let's imagine we have our UV coordinates again. So we have our 0, 0 and our 1, 1. We could try and use those two positions to basically just define like our distance from 0, 0 and then normalize that value. So essentially what we want to do is like say have this value, if you're over here, be defined as 1, and then this value be defined as 0. And then if you're like at this halfway point, we'd want this to be like 0.5. So what we could do is just take u plus v over, what would it be, like root 2, I believe? Something like that. And that should give us, I think that math checks out. Does that sound correct? Because like this whole distance would be, oh no, it'd be u plus v over 2, I believe. Yeah.
Would be what?
So essentially, I'm just trying to make like a gradient effect. Let's just try this out. I think u plus v over 2 should work. But basically, we want this coordinate to be normalized to 1, and then this coordinate to be normalized to 0. I don't know if this is necessarily the correct way to do it, but we'll try it out. Let's see what happens. So instead of doing this, I'm going to do color times I dot u v dot u plus, wait, is that the correct way to do this? Let me double check. On X and Y, I think. Again, I'm not sure if this is the correct syntax off the top of my head, but essentially the idea is that based on our UV coordinates, we're going to try and make one end be a full color, the other end be essentially black because we're multiplying the color by 0. Number 2. I don't know if this will work. Let's see if we get an error. Yeah, we get an error. What did I change? Oh wait, I need to put color here. Let me back up a bunch. Or color. And what I have before. Jesus. Okay. Color times I dot UV
Dot X.
dot. I don't actually know if I can access that directly, or because UV
I'm pretty
is.
sure you accessed it in the other one, didn't you?
Yeah, I think so. Let's just try it. UV dot X plus I dot UV dot. I might be like UV of 1, maybe. Because okay, it's a float 2. Let me see how I access other values here. P. Okay, yeah, it's just dot X and dot Y. Yeah, the annoying thing is that like a lot of the syntax is a lot different than other languages, so it gets a little annoying to like have to cross-reference everything. But it's just like using any other new language. Okay, so that. Why is it? Why is it mad? Oh, I need a colon there. That's why. Always the semicolon. Okay, cool. That worked. And then let's go back to our other scene. Tests. We'll save this for now. Okay, cool. Yeah. So you can see we get this sort of gradient effect that occurs. So this is obviously not like as complicated as the lighting effect, but essentially what's happening is our we're just multiplying by a factor that changes the color. So we're just grabbing how far we are from the 0 coordinate, which I guess is mapped to this top corner on this texture, but on this texture is mapped to the bottom corner. And we're using that to essentially make a gradient across the side. Does that sort of make sense?
That looks so trippy.
It is kind of weird.
Are you able to just change the color in the editor?
Yes. So if we go back to our material, say we make it something like this, like yellow, for example.
So if you have complicated enough math, you could like conceivably do like whatever kind of weird thing you want to do.
Exactly. And I'm not in the mood to talk about a bunch of complicated math right now. Well, I am, but like I'm gonna spare
Mark, you're always in the mood for that.
you. Anyways, so this is just kind of like a very basic introduction of like how you can manipulate pixel data from like a UV texture, for example.
Any questions?
Yeah, any questions? Okay, I'll take that as a no.
Wait.
Oh, okay.
Can you go back to how you implement the color within Unity? Because I'm trying to do it in my code, but I'm getting errors and it's not working. So.
Sure. So all I did was I made a new material.
Right.
So you have the material, do you have the shader as well? And then all I did was just drag the shader onto the material. And then from there, in the material, you should see like a color value there, assuming you set it up correctly. I'll show the code again.
When you go into the material, you should see a color value, right?
Yes. Below the texture.
I don't see that. That's why.
Okay.
Do you have to define it in properties, right?
Yeah. Are you getting any? Yeah. So we have it defined in properties here.
Should there be a colon at the end of that or no?
Right here there should be. So okay, I defined these are the lines I changed. So I added
added color.
Added color. In pass, I added fixed for color, and that grabs the value that's passed into properties, which is in turn passed in from the shader or from the material, pardon me. And then I changed this line from what it was before to be that color value. So those are the only changes that I've made.
Am I correct in thinking that properties is almost like a little database of information which you can then draw from in multiple pass type of functions?
Yes.
To define your variables?
So pretty much, yeah. So it's attached to the shader itself as just kind of like every individual pixel will have that same data. But other information is unique to the pixel, and that's kind of what's covered in pass here, like position, textual coordinate, all this kind of stuff, for example. A lot of this is pretty math heavy, so you have to read through a bunch of documentation to like fully understand like what each of these refers to. That's me just saying that I haven't read the documentation, so I don't know it off the top of my head. But
does pass apply to like every pixel on the screen? Or every pixel? Yeah. Which pixels does pass apply to?
It applies to every pixel that is intersecting with the material, or sorry, intersecting with the object on this material. So for example, if we zoom in, like all of the pixels, almost all the pixels on the screen are intersecting with a plane that's defined by this material, which in turn is defined by the shader. So all of these pixels are colored by that shader. But as I zoom out, like only this region is defined by this shader. So only this region will be colored that way. So this is a it's a like object mesh-based shader, whereas there's also post-processing shaders which apply to a texture after everything's been rendered. So I'm going to go into that now.
Would you ever have multiple pass functions for the same shader?
Yeah, you can put multiple shaders on an object. So that's actually kind of what shader graph does, and we'll.
So subshader means it's a shader.
Yeah.
And you can define multiple shaders within. I'm just trying to like figure out why you have to redefine the variables.
What do you mean?
It doesn't make any sense to me. That you'd have to define the properties and then do it again.
It's just kind of the syntax of how the shaders work. I don't really have an explanation behind the reasoning for that, but anyways, so what was I going to go into? Oh, right. I want to talk about post-processing shaders. So again, these are shaders that are defined on meshes, but we can also do shaders that affect the entire image. So for example, like if I wanted to do something with this gradient effect across the entire image, what I'd have to do is essentially sample the rendering once it's done and then apply a bunch of data to it afterwards. So if we go back to the sound wave effect, for example, I'm just going to run it for a little bit and pause it while there's a wave effect. Oops, I want to go into the game still. So essentially what's happening here is I'm first rendering the scene. So actually here, let me play it. We'll keep it playing. I'm trying to think. Okay, I'm gonna conceptually explain what's happening here first. So I don't think you can hear it because I'm not sharing audio, but essentially there's two sort of drum beats that are bouncing off of these two objects here. And what's happening is every time they're above some amplitude, the position of that sound is sampled and then sent into a shader, which then makes that wave effect from that position. So you can see like every time the drum beat hits, and you can test this on your own version as well, a wave will emanate from this object. So if we look into the actual camera, there's two scripts attached to it. So there's a sound sampler that's just finding where all the sounds are in the scene and like actually sampling from them. And then there's the sound wave effect, which is actually handling how this wave effect is drawn. So if you look on this, it's set up pretty much like a normal game object in that, or a normal script in that we have just a bunch of variables here. But you'll notice that we have this effect material of sound wave effect attached on this object. So I'm gonna stop this because this drum beat is annoying. If we look at our sound wave effect, it's actually, like we set up before, another material. So what this material does is a bit different than that other material that we had just defined before, because it samples a texture, but the texture that it's sampling is actually the entire screen. So every time a frame is rendered, what's actually happening is it's defining essentially a texture that is then mapped onto your screen as an image. So what we're doing is we're sampling from that texture, using data about it to then add some other effects to it, and then passing it back through and rendering it as a complete image. So if I run it again, you'll see if I go to the main camera and I disable the sound wave effect, all it's doing is just rendering the scene as we were seeing it before, right? But as soon as I turn it on, it's running all this post-processing that actually renders what these wave effects are doing. And how these waves are actually being rendered is essentially the camera has access to this data called a depth buffer, which if we go back to our diagram of this frustum, essentially the depth buffer is your distance from the camera, or sorry, from the front region to wherever your object is. So we define this kind of front position as 0 and this back region as 1. And every object will have some depth value based on its pixel position. That is some value between 0 and 1. So for example, this might be like 0.8. If we had another close object right here, this might be like 0.1 or something like that. So every pixel will have some depth value to it that's attached to the camera. And there's a bunch of other things that are kind of similar to this that are just like data that's collected every frame that can be used by shaders. And you kind of just learn more about them as you like mess with shaders more. But this is a very useful one because essentially what we can use it for, I have to stop saying essentially. Essentially what we use it for is calculating where in a scene the depth of every single pixel is relative to another position. So you can imagine, let's back up a bit. So say I have a, if I want to make like a wave effect that's kind of like emanating from the player away from them, right? So you can imagine, it's hard to like explain this in words, but think of like a wave moving away from you. One way that you could do that is by using that depth buffer and say coloring all of the close pixels initially coloring all the close pixels with some color, say like white, and then within some region color every pixel that's like from 0 to 0.1 white, and then next frame do like 0.1 to 0.2, color all those white, and so on, and just repeat that by expanding out a wave. And what would happen is we'd go across this whole scene and just kind of color it a chunk at a time with whatever color we wanted to do. So the problem with that, though, is that it's linked to the camera's space. Is any of this making sense, by the way? Because I feel like I'm kind of rambling, but is everyone kind of following along? Or any questions? Okay, cool. Feel free to stop me in the middle if you're just like completely lost, because this is a lot of information that I'm just kind of like throwing around and jumping around to. But anyways, let's back up. So we have our frustum. and our camera. And we have our depth buffer. So our depth buffer, again, tells us how far an object is from the camera. But remember that this whole scene is rendered in an object space relative to some origin position. So we have our X, Y, and our Z. So the camera has some position over here. We're doing a bit of vector math, so bear with me. We'll call this just like V sub C or something like that. And our object has some other position. We'll call it like V sub O. And we can tell from the depth buffer how far this object is from the camera, because we know the size of the frustum, we know the multiplier of like how far it is from the camera. We can essentially define this vector based off of just the camera position and the object position. But what we can do is actually use these two vectors and add them together to get the position of this specific pixel on this object in world space. And the reason that's useful is that we can then kind of decouple our whatever effects we want from the camera and define them entirely in world space. So if you remember when I was explaining before that like wave effect as it's emanating away from the camera, if you were like a player in like a first person game, like rotating your camera, that wave would be stuck based on where your camera is in the scene. So thanks, Evan. Basically, if you were to rotate your camera, that wave would keep emanating out no matter what direction you're looking because it's tied to your camera. But if we can instead define every pixel in world space rather than in camera space, we can, for example, have some position here and emanate out a wave from it that basically just kind of samples all these pixels here. And if these pixels are like a certain distance from that position in world space, because we know this world space position and this pixel's world space position, we can color that based on the distance between it. Does that make sense? This, again, this isn't possible from just the camera position, because if I were to like rotate my camera, then this position would subsequently rotate with the camera. So we want to decouple it into world space.
Yeah, if I'm understanding correctly, so what you do is you take the vector from the camera to whatever object you're looking at, add it to the camera's vector position, and then that will give you the world space position of the object, and then you
of the pixel specifically, because we already know where the object is in the scene. That's not really relevant. What we're trying to do is actually define our entire screen in world space based on the pixel positions. So
then once you do that, and let's say you wanted to make a wave like you're showing in the diagram, you would say, okay, now color the pixels that are however many like other pixels away from that the original one, I guess is what I'm saying.
Exactly.
Okay.
So here, I'm just gonna pause and take a screenshot of this, for example. Let me see. We'll use the old snipping tool, and I'll draw on top of this, so that makes a bit more sense. Because I can't draw directly on my screen. Okay. So we have this whole rendering, right? So what we've done with the sort of sound is we've selected the position of where that sound is emanating from, and we're defining this entire scene pixel by pixel by its distance from the camera. So for example, like a pixel right here would be much closer to the camera. This might have a value of, I don't know, arbitrary like 0.1. Whereas off in the distance where there's nothing rendering, these would all have a value of 1 because they're at the very back end of the camera's frustum. Whereas like a pixel here might have a value of like 0.6, and then something back here might be like 0.8. That makes sense, right?
Yeah.
So what we've done is, say like our origin's over here. I'm just gonna scroll down a bit. Let's say our camera is, obviously it's not actually here, but let's say our camera is like right here, rendering the scene like this somehow. However it ends up working out. So what we're doing is we're again, from this origin position, we're getting the camera's position and the position of each of these pixels, and then using that addition to then get the actual world space position of each of these rendered pixels. Make sense?
Yeah, wait, so so each pixel, the camera knows like the distance, it already knows the distance each pixel is away from it,
Yes.
kind.
So that's just like a built-in feature of the render pipeline. You get this depth buffer that keeps track of all that information, because it's essentially like that's all calculated for free as part of another part of the render pipeline. So that data is stored because it's useful for stuff like this.
Okay, wait, so would it get that information from just like shooting out a bunch of vectors from the camera and seeing what it hits or something like that?
So essentially that data is generated somewhere else as a byproduct of another step. So you can imagine, like, if I want to render a triangle over here, I need to know like where each of these pixels is relative to the camera. So that data is kind of generated as another step from another part of the render pipeline, and then saved in a buffer so that you can use it for applications like this. So it's not actually, we're not gathering all that data frame by frame, because it's already generated as part of the render pipeline. Not every render pipeline actually defines this depth buffer, but it's essentially free information that's stored within the camera already. And there's other stuff like that that's just like free data that's stored with the camera. Like you can access from an image every single pixel value's color, for example. And like, say if you want to get rid of, or if you want to like tint everything red, you could just like apply kind of a red filter on top of everything, sort of like what we did with that gradient, just by like multiplying by a red color or something like that.
Okay, all right, I see. All right, thank you.
Cool, yeah. Anyway, so the whole reason that we wanted to like get the world space coordinates is because it's much easier to do this whole calculation of like, I have some position of a sound here and I have 2 world space positions. I can then just subtract like this position and this position to get this distance between these two, rather than having to figure out like where this is relative to the camera and then do a bunch of other math, or essentially using a resource that's already there to kind of get a calculation for free. And then now I can move my camera around and I know the world space coordinates of all these different things. And I can then just kind of like add on these colors based on like their distance from a source. Okay, does that sort of make sense, like what the reasoning behind all that is? Are there any questions? Okay, I'll take that as a no. Okay, now I'll just kind of walk you through the actual implementation of this. So I'll preface this that I basically used the code for a similar effect to this, and then kind of modified it to make it so that it could render like multiple at a time. So a lot of this I had actually sourced from, I think I have the video open still. Essentially this video on making a shader effect on from No Man's Sky. So you can see like they're doing kind of a similar thing here of like a wave emanating out from the player. That was kind of what I was referring to earlier. But anyways, I modified the code from that to make this effect essentially. Anyways, that's just kind of like to cite my source, I guess. But if we go into the code, wherever I put it, let's see. Okay, so this is the actual shader that I've defined here. So we can see in our properties, I have just a ton of different variables here. So it has a texture, a scan width, which define, I'm just going to put the code next to this. So, oops, what did I do? Oh, yeah. The scan width is essentially just like how wide this region is here. Edge sharpness, that kind of is like that'll make sense later. Bar width, that defines like how wide these kind of like stripe patterns are. And then there's like a set of different colors that are kind of all combined together. And what's happening is, again, I'm just going to kind of gloss over this because it's not too relevant to what we want to actually talk about here. This is all just kind of like the setup code. I'm not even really sure what's happening here. So a lot of the time that'll be kind of pre-generated for you. At some point I want to actually like know what all that means, but that's like, I have classes to take. So anyways, so again, we go through, define all those variables. I'm gonna pop this back over here actually. And what I had done is I basically added in this just like arbitrarily sized array that keeps track of a set of world space positions, which are like the sources of where all those waves are emanating from, and how far each of them has traveled. And the reason is kind of like this clunky design is because essentially shaders need to be passed a fixed amount of data. You can't pass them a variable amount of data just because of how they are implemented as a function for a graphics card. So this is a little clunky. I want to try and figure out a better way to do it, but I haven't read too much into it. But anyways, so it's just like this arbitrarily sized array that keeps track of a bunch of positions. And this is like some fancy math that basically adds all those kind of horizontal bars that are emanating from the center of the screen there. That's not really relevant. It's some like trigonometry, basically. But I gave you guys all this code, so if you want to like poke around it, and if you have any questions about it, feel free to ask me. But let's see. So what's happening here? Remember that the frag shader is what's the important one. So what I do is I take in the main texture here. When okay, let me back up actually. So where I'm grabbing this texture from, if we look onto, remember back here, if we look onto the main camera, we have this sound wave effect script that's on here, as well as this material. So if we look into the sound wave effect script, it has all those variables defined there. In start, it sets a bunch of them as it is. In update, basically what it's doing is it's just defining all those different positions and feeding them into that array that we want to pass into the shader. I can also like click on the screen and create a new thing. So update's just kind of like sourcing all those different positions. You can look at the code in more detail if you'd like on your own time. But it's also doing this thing called onRenderImage. So this is a specific function to Unity that essentially, if you look at the definition, it's called after all rendering is complete to render an image. So what that means is when you've rendered an image, essentially like what you see on the screen, that's a texture, and we're sampling that texture and then passing it into a shader, applying some effects to it, and then passing it out again. So that's what all of this code kind of is doing. So we're grabbing the existing rendered texture, using that depth data to analyze a bunch of it and apply some colors on top of it, and then passing it back out and using that as our final output. So these calls are basically just passing in that data from the script into the shader, into the material, which then passes it to the shader. This does some fancy stuff. This is all a bunch of just like matrix math that defines how to actually capture that texture. You don't really need to care about this because again, I just kind of like grab this from somewhere else. But anyways, conceptually, all you really need to know is that this script is grabbing the texture and passing it into the shader. So it grabs that whole rendered texture, passes it into the main texture here. Excuse me. And then all I'm doing to it is I'm defining some grayscale value. So remember, we're doing this pixel by pixel. So I can grab the red, green, and blue values from my specific pixel that I'm looking at, and then average them out to get a grayscale value, and then set all of those, set my color to each of those grayscale values. So essentially, this is just kind of, I also added a multiplier here to make it darker. That's what's causing this effect of like the whole screen going kind of gray when I enable and disable this script. Essentially, it's just sampling all the colors, averaging them out, and then turning it gray. So that's similar to what we were doing actually with the gradient effect, except just like different math that achieves a different effect, where we're just changing the color value based on some information about it. And then this is the fun part. So if we look here, so that does all the grayscale stuff. This is what's handling that whole world position translation. So first, we have our camera depth texture, which is another thing that was passed in. Or, sorry, this is just kind of given for free. So if we just define it here, it will grab all the data that's available. This is a function that's built into Unity that essentially will just grab based on, what am I looking for? It will grab that texture data and your UV depth and then it will get you the depth of that actual pixel. Yeah, so this is grabbing the pixel depth. This linearizes it essentially. And then what we're doing is we have a ray that's passed in that is cast from the camera to that position on the pixel. And we're just multiplying by the depth value at that point. So if we look here, for example, God, this is a mess. It's going to erase some of this. So if I'm looking at this pixel, for example, part of the data that we're passing into this is essentially this ray to that pixel, which is defined as some just vertex. And you can see that is defined up here somewhere. Yeah. So again, most of this is just kind of like we're passing an array that's eventually defined as interpolated array. And then all we're doing is just adding our world space of our camera position, which was passed in before as well, to our world space direction. And then that just gives us the vector that defines the position of our pixel. And once we have that, we can do some interesting math to make that wave effect. So you can kind of ignore this for loop. That's just kind of checking over every single one of the wave effects. What we're going to do is just check how I had it defined is like the array's default to 0. And if it's not 0, then that means there's something in it. And basically we grab our distance from our world space position of our pixel to our source, which again is just passed in as data. And then if our distance is between some range, which would be our scan distance, whatever its current value is, which is passed in, and our scan distance minus the width of the scan. So essentially like an outer edge and then a region before it. And our linear depth is less than 1. That's essentially just like that cuts it off in case it like ends up at the back end. All of this basically just defines that whole region of a wave. So if you're in this, if your pixel is within that range, then you'll define it as some color. And all this is doing is basically just kind of defining what that color is. So this gets our difference between those positions. And based on that difference, we're going to do a Lerp, which is a linear interpretation between 2 points. That essentially just kind of like averages based on 2 data points between 2 things. So if you have like from 0, 0 to 1, 1, and you Lerp at 0.5, you'll get the value 0.5, 0.5. Or like if you Lerp at 0.3, you get 0.3, 0.3. It's essentially just like taking whatever linear interpolation between those 2 points would be. So what we're doing to what we're using that for is essentially like our distance from the edge. We will Lerp between the 2 colors that we kind of passed in. So if we look back at our material, we pass in a bunch of different colors. So a leading color, an edge, and essentially a back color. And eventually, basically all this is just kind of doing some math to make this kind of cool looking effect of the wave going across a bunch of different colors. That was a lot of information, but that sort of makes sense as to like how you can do a more complicated shader. And I'll admit also, like, I spent like weeks on this and I kind of just brushed through it. So if this didn't make any sense at all, then like I can explain a bit more detail or in a bit more detail.
I guess just in terms of making it a little simpler, if you had like a 2D game and like you wanted to emanate a wave, like a side scroller, and you wanted to emanate a wave from the player, you would use shaders for that. And if you would you use shaders for that, or is there something else?
It depends on like what effect you're going for, because like something like that could easily be done with just like a texture that you grow in size or something like that. Something like this is more useful because it can be dynamically scripted. So the reason that I did this was because I wanted it to like sync up with sound in the game, and that's like hard to do otherwise, I guess. So that's why I wanted to like look into shaders to do the specific effect. But
no, I
yeah,
guess my question is more about the applicability of where you would use them and when you wouldn't.
Yeah, so this is like obviously a very, very specific example of like a shader that's done for like a specific application. But you could imagine like you could do something similar if you wanted to think of like what's an example? If you played Overwatch, like Winston's shield, the like shield ball that he drops, something like that could be done with a shader similarly by defining a region around a sphere and then kind of like adding a particle effect based on like how it intersects with other meshes. That's an example of like something that could be done with a shader. Other things, if you wanted to add like post-processing effects, kind of like what Athena had covered in the art tutorial, a lot of those are implemented using shaders where like if you want to add a blur effect, you can basically do something like sample the depth of distance and then say if it's within some range, don't do any blurring. But if it's not within some range, then you can kind of like average over a region around a certain pixel, for example. Essentially, it's just kind of like you learn more uses for it as you kind of research it more. But yeah, this is definitely a more complicated example than I probably should have started with, but I just kind of want to show it off. So, okay. Are there any other questions? Oh, I see. Does Unity have an exponential interpolation function beyond Lerp? Probably. I don't know off the top of my head. I'm sorry. Yeah. Anyways, that's pretty much everything I had prepared for today. If you can call that prepared, but hopefully that gives you like a brief introduction into like what shaders can be used for and like how they're implemented. So again, I had mentioned before that like shader graph is a tool that's within Unity that makes this like way easier. So I don't actually know how to use it off the top of my head. I tried it out like a couple years ago and like haven't touched it since. But essentially all of these like complicated effects that like look like they involve a ton of math can be sort of added together in different ways. But shader graph makes that easy by like putting it all into a UI. So you just kind of like drag and drop different effects and combine them all together. So it's useful to kind of know like what's going on under the hood as far as like, oh, what's actually happening is like each individual pixel is being rendered using like a bunch of math. But yeah, the actual sort of like artistic implementation of it is a lot easier just because most of these tools have been either like already implemented by someone else or can kind of easily be added on to by doing something like this essentially. But yeah, so that's sort of the basics of shaders. Are there any other questions?
So the shader graph, that's what it's called, right?
Yeah.
Is it kind of like I heard about they released a new thing. It's for like coding that makes it easier for people to use or something. It's like Bolt or something. It's called Bolt, Unity Bolt. I don't know.
Oh,
but
I vaguely remember hearing about that as well.
yeah, is it sort of like that maybe, but for shaders?
Yes. So here's like I just pulled up the page that they have on.
Oh, it is. Oh.
Yeah, it's basically just like drag and drop a bunch of different effects.
I see.
But it's super powerful and a lot easier to do than all this kind of low level stuff. But the thing is, it's like difficult to do something like the effect that I explained here with shader graph, because shader graph is more tuned to, or as far as I know, more tuned towards specifically like object shaders rather than like post-processing. So yeah, like they mentioned, traditionally in the realm of some of programming ability, this makes it so much easier to just kind of like throw stuff on together. So actually, if you guys are interested, I'd be willing to learn this in a weekend and then kind of teach you guys some of it if that's a future lesson you guys are interested in. I can scope that out later, but
yeah, I think that would be cool.
Okay, I'll keep it in mind because we have like 4 or 5 more lessons to go. Actually, while I'm on that topic, are there any other like interesting topics that people have kind of seen come up that you would like to see a lesson about? I have a lot of just like scattered knowledge about like little bits of Unity, so I can probably try and throw something together of like intro level.
And then what were your other tutorial, like what other tutorials do you have that you might be planning on making?
That was a great question. I don't have an answer to that because we're kind of just like winging it, but I know there's interest in like networking, but that's kind of difficult. Also I think we wanted to do one on like coroutines and kind of making your code more efficient as well. Yeah, I'm still kind of, we had to plan some stuff out, but it's also midterm season, so we'll see.
Yeah, it's true.
Okay. I'm going to stop the recording as well, just because pretty much done. All right. Thank you for coming, by the way.
Yeah, thank you for